Hello and welcome to this video on solving rational equations. I'm going to show two techniques in this video. It's decently lengthy. There's 4 examples. The examples are decently long. If you want to go right to a particular example, just look at the time signature on this page next to the examples below, and you can fast forward. The two techniques here are going to be multiplying both sides of the equation by the LCM of all the denominators. That's a technique or a trick I'll employ to solve some problems. And the second is getting a common denominator using the LCM and canceling it. Now, if you notice, there's LCM mentioned in both techniques. If you're not good with LCM and variable expressions, it's going to be a very difficult video for you to understand. So you need to bring that to the table when you're doing these problems. Okay, so solve and check for extraneous solutions. I mean, this is an example, like I said, about multiplying both sides of the equation by the LCM of all the denominators that appear in the problem. Extraneous solutions are ones that we generate by doing due diligence to the properties of equality, but when we check them, they don't work. So it doesn't mean we did something wrong in finding it. It just means we have an additional answer that doesn't help us because it doesn't make the equation true, so you just toss it out. And you should have some experience with those already. All right, so to start, if we talk about the LCM of all the denominators in the problem, you have to realize that these guys have some terms that don't look like fractions but are. So when I'm really doing x minus 28 over x equals 3, I could kind of view it like this. Then we see that the LCM of x and 1, which is all the denominators in the problem, is just x. So I will, in fact, multiply both sides of the equation by x. It's going to take some distribution here on the left side. Okay, so I'll use some colors here, and we'll get x times x is x squared, and then the purple one is just minus 28. Other side's going to be just 3x. If you're curious how I got the purple number, if you notice it was x times negative 28 over x. This is x over 1. The x's cancel, and you're just left with the negative 28. Okay, you have to be able to multiply fractions and see cancellations as well when you're doing these problems. So now that I have a quadratic, I will just try and set the quadratic equal to 0 by subtracting 3x from both sides. And then I notice here the factors of negative 28 that make negative 3 are available to me. It's 4 and 7. So I'll set up 2 binomials, 4, 7. And then I go, I want the middle term here to be negative, so the bigger term is negative. And this should not be anything out of the ordinary for you. It's just the zero product property at this point. So I get x equals negative 4 and x equals 7. So in checking both of those answers, if you notice, I'll get negative 4 store x, and look at the original problem, which is x minus 28 divided by x, and hope to see 3, and I do. Then I'll do 7 store x, and then I will get the original problem back, and we see that that also yields 3. So there's no extraneous solutions here. So my answers are, in fact, x equals negative 4 and x equals 7. Again, this is an example of multiplying both sides by the LCM of all the denominators in the problem, being mindful to realize that if you don't have a denominator that's visible, it really is just 1. Okay? Okay, let's look at this second example of solving a rational equation and checking for extraneous solutions. Again, we're going to be talking about multiplying both sides by the LCM of all the denominators. Denominators are not that complex. They're not binomials or trinomials that need factoring to help identify the LCM, which I'll do in the margin now. The LCM, if you're looking at the coefficients of 1, 2, and 3, is going to be 6. And if you're looking at the variable terms of r squared, r cubed, it's r cubed. You need the biggest exponent when you're doing least common multiple. You should have that squared away if you're already watching this video. So let's multiply both sides by 6r cubed and see our result. Okay, so given this distribution, we've got 6r cubed times 4 over r is going to give me 24r squared. And then 6r cubed times 3 over 2r squared is going to give me 9r. And on the right side of the equation, we get 18 because the r cubes cancel nicely, and you get 54 over 3, which is 18. So here now I just have a quadratic. So I'll try and set it equal to 0 by subtracting 18 from both sides. If you notice here, you can take a second and divide both sides by 3. It'll help get you to deal with smaller numbers. You're not losing any solutions because you're not dividing by a variable. And that is going to give you 8r squared plus 3r minus 6 equals 0. Quick check for factoring. You're going to get the negative 48 in that product of a and c. I don't think they're factors of negative 48 that make 3. So I'm resigned to doing the quadratic formula here. So we've got an ABC chart. It's 8, 3, negative 6, giving me x equals the opposite of b, plus or minus the square root of b squared, minus 4ac, all divided by 2a, okay, which is going to be x equals negative 3, plus or minus the square root of, not a bad time to go to my calculator, and do 3 squared minus 4 times 8 times negative 6, which gives me 201, all divided by 16. 201, I know it's divisible by 3. Its buddy factor is 67, which is prime, so I'm convinced I'm going to need to leave that there. And just to take a second, I'm going to pop these in on my calculator. I'm going to pause the video and come back and show you the screens, and we'll see if these work. So just a quick overview for time here. You started out using the store button, okay, for the first of these two x values, right? The only thing you got to be careful of now when you are doing this equation is making sure you use your parentheses in the denominators, okay, in terms of making groups for the denominators. And if you notice here, when I plugged in the plus here into the calculator, the left side and the right side are both equal. Similarly here, when I did the negative stored on the calculator for x, I did generate two values that were the same, showing that the left side and right side are equal again. So both of these answers are totally legitimate. There's no extraneous solution, and this is the solution to this rational equation. Okay, this is the third example where we're going to solve and check for an extraneous solution in a rational equation. I'm going to use a little different technique here than the previous two. These problems, I think, as the denominators get a little more complex. We've got some monomials, some binomials. I'm actually going to get a common denominator using the LCM, okay, and then cancel it all out by multiplying both sides. So let's take a look here what the LCM is going to be. The LCM, in this case, is going to be gotten by looking and making sure that every unique expression in each denominator is accounted for in the product of the LCM here. So it's actually just going to be x times x minus 3. And I won't actually multiply in this x because it's already represented when I represented this x. So no need to be sort of redundant here. This is a totally legitimate LCM. If you don't have that skill, you're going to need to look for it. So I'm going to now get a common denominator here, which means I'm going to take each term on both sides of the equation and convert their denominator. So it's a little bit of writing. I'm going to try and give you a little color here. One of the things you see here is in this first denominator, it has x, but not the x minus 3. So I'm going to multiply in an x minus 3 to this first expression. Okay? Now, the big idea here is that this number is 1. Anything over itself is 1. So when I multiply this 2 over x by 1, I haven't really changed it. And that's the big idea there. Okay, so we're going to go to subtract. Okay, and then we're going to examine this next term and realize that it has the x minus 3 in the denominator, but not the x value. So we're going to multiply that in by doing x over x times 4 over x minus 3. Okay? So, realizing that's going to take some distributing. And then on the right side of the equation, again, where we see it has the x, but not the x minus 3, we're going to multiply in the x minus 3. The order that you write these doesn't particularly matter. So, I'll write the expression 10 over x, and then x minus 3 over x minus 3. And again, I'm just multiplying each term by 1. So nothing's really changing. Okay? Now, that being said, let me just kind of move this over and group it, because what I'm about to do is going to be a little bit extensive in how much room I need. So now, if you notice, I have a common denominator in every term. And this is wonderful, because now what I'm really going to do is I'm actually going to multiply by the LCM, like I was doing before, but I got a common denominator first. So if you notice now, I'm going to multiply by x times x minus 3 on both sides. Now, this is great, because if you realize it, I'm just going to be able to cancel the entire denominator here. Because when I take this and multiply it by this expression, it's going to cancel the denominators. And then when I multiply it by the second term, it's the expression there, it's also going to cancel the denominators. Now, don't get weirded out by cross this out twice, because you're doing distribution. So that you canceled it for the first term, then you got to look at it for the second term, which it just cancels again. Okay? So then over here, there's really only one term on the right side, but it in fact is going to get canceled again, leaving me just with x minus 3, the quantity, times 2 minus 4x is equal to 10 times x minus 3, which is totally solvable equation now. It's almost something from like 7th grade. So I'll distribute here and get 2x minus 6 minus 4x is equal to 10x minus 30. And then that's going to give me negative 2x minus 6 equals 10x minus 30. I'll add 2x to both sides and get 12x. Negative 6 equals 12x minus 30. Go here for space. I'm going to add 30 to both sides, get 36 equals 12x. Excuse me, no, I'm going to get 24 equals 12x. Dividing by 12 on both sides is going to get me x equals 2. Okay? So it's only one answer to check. I'll do 2 store x on my calculator. Excuse me. 2 store x on my calculator. Let's see if this works by doing 2 divided by x minus 4 divided by x minus 3. And asking myself, is that second test equal to 10 divided by x? The calculator says 1, which means we're done. If it said O, it would mean it's no. So that means that x equals 2 is in fact the solution to this equation. It is not extraneous. It is the value that makes the left side equal to right. All that good stuff. It's wonderful. Okay, here we are on the 4th example, where we're going to solve and check for extraneous solutions in a rational equation. Again, I'm going to try to use the technique of getting a common denominator via the LCM and then canceling it out. It almost looks like magic when I cancel it out if you saw the last example, but it's pretty powerful stuff if you can realize what's going on behind the scenes. So we have x over x minus 2 plus 1 over x minus 4 is equal to 2 over x squared minus 6x plus 8. Well, it may not be obvious, but the one thing we probably want to do here when we're dealing with LCMs is deal with factors. So this guy in the denominator right here might want to get re-expressed. Probably just a little trick you're noticing already that a lot of these problems are engineered where you might see these terms again when I factor it. So let's take a look. We're going to get x over x minus 2 plus 1 over x minus 4 is equal to 2 over, when I factor this, I'm looking for the factors of 8 that make negative 6, and they are, in fact, x minus 2 in quantity times a quantity x minus 4. So when I'm looking for the LCM here, the LCM is really just going to be x minus 2, the quantity thereof, times x minus 4. Okay? So that would just be gotten by taking these individual factors and multiplying them together, which you would then wind up with the denominator that you see on the other side of the problem. So in using that common denominator, I just got to look and say, using that LCM to make the common denominator, that is, this x minus 2 is missing the x minus 4, so I'll multiply that in. I'll change colors for you here. So we're going to multiply by x minus 4 over x minus 4. Now I'll need those parentheses here. Again, you're multiplying by 1. So when you have this term here, and you're multiplying by 1, you're not really changing anything. That's why this is all legit from a why you're allowed to do it standpoint. Now looking at the next term, 1 over x minus 4, I see that it does not have the factor of x minus 2. So I'll multiply that in by multiplying by x minus 2 over x minus 2, which again is 1. And I'm going to multiply that in, where we have 1 over x minus 4. Now, don't let the fact that I sort of change the order here, red, black, black, red, throw you off. It's still multiplication, so the order doesn't matter. Do it whatever way you are comfortable. Okay, now on the right side of the equation, I don't have to multiply by anything, because I, in fact, have the appropriate denominator here. Okay? So, now, where does that leave us? That leaves us, if you notice, that you've got the appropriate common denominator in all three terms represented in the problem, the two terms on the left and the one term on the right. Well, then, hopefully you'll realize that you can multiply both sides by that LCM, which is now the common denominator. And it really, in fact, just seems like it does a big magic canceling, because these two factors times the first term will just cancel the ones on bottom, and these two factors times the second term cancels the ones on bottom there too, leaving us with just x times x minus 4 plus x minus 2 times 1, well, that's just x minus 2, is equal to, canceling on the other side, 2. Okay? So that gives us x squared minus 4x plus x minus 2 is equal to 2, which gives us x squared minus 3x minus 2 equals, 2. And then, scrolling down to get a little more room here. Again, I'm just dealing with a quadratic, so I'll get it all set to 0. Subtracting 2 from both sides gives me this. And now, what are the factors of negative 4 that make negative 3? Lucky for us that it can be factored. 2 terms of x here. I'll use 1 and 4, and to get the middle term to be negative, the 4 needs to be negative. Makes you value having become a good factor. X plus 1 is 0. X minus 4 is 0. Giving us x equals negative 1 and x equals 4. Okay? So the only piece of that is now left for me to check is using my calculator to see if either of those values are extraneous. Okay? So I will do negative 1 store x, and we shall see how that works out when I do x divided by the quantity x minus 2, so you need parentheses, right, plus 1 divided by the quantity x minus 4. Okay? Is that, in fact, second test equal to? Okay, because I haven't rounded any of these answers, so it's a great time to use that second test feature. 2 divided by, left parenthesis, x squared minus 6x plus 8. And 1 is done and 0 is no, so we know that this x equals negative 1 is in fact good. Now, I'll tell you a little secret that I know the 4 is bad already, and not just because I did the problem, but I'll show it on your calculator. 4 store x. And then we'll go second enter twice to pull up that previous line. And then it actually says, error, divide by 0. Well, I kind of knew that was coming. Because if you notice here, this value of x equals 4, when plugged in right here, well, in all x's really, but in this second term, you'll notice you would get 1 over 0. So what it becomes in the other terms doesn't matter, because in that second term, it creates an undefined number. And this is a good example of an extraneous solution. So here we go that we have found x equals negative 1 is good, x equals 4 is bad, so we throw it out. All right, so I hope this is a help to you. If you notice these two techniques used together, I'll go back to the first slide. Okay? There's places where just multiplying by the LCM on both sides is sufficient. If you notice, there are usually places where the denominators aren't so complex. Okay? And if you're wondering where's a good time to get a common denominator, it's when the denominators become a little more complex. Usually you see binomials, trinomials, things that need to be factored. Now, these are just suggestions. You can really do this sort of any way you want, as long as you do whatever you want on both sides and don't break any rules. This is just trying to modeling some examples and some techniques that I use. You have to get a feel for them, when to zig, when to zag. Knowing that takes some practice.